So today's topic is error correction and error detection. So error detection and error correction. These are two topics that we need to talk about whenever we transfer data from one place to another place. So let's say you have a transmitter, it sends some bits, but over the air at the same time there was some interference and some bits were sent in a wrong way. So there are some bit errors in the transmitted packet, and the receiver needs to be able to detect that there are some errors and probably either delete the information because it's false, it's wrong, or maybe send back to the transceiver that there was some error and ask for retransmit. So let's see how we can do it. So we have a transmitter TX, for example, with antenna. But the same thing works even if transmitter and receiver are connected with a cable. Even in cable communication, there can be some noise in the cables and some bits can be sent in a wrong way, and they still need to be checked and errors need to be detected. So we have transmitter, receiver, and transmitter sends some information. You know, 1 byte. And let's say there was some noise which changed the bit from 0 to 1. Some noise, some interference, other transmitter sending at the same time or something. So the question is, how can a receiver detect this error? And let's look at the classic error detection algorithms. And the first one is parity. So, parity. Parity basically counts the number of ones and tells if the number of ones is odd or even number. And so we can just add a parity bit at the end of our byte. So we sent 1 byte is 8 bits. And then with blue, we will just add parity. The sender adds parity. So instead of 8 bits, we actually send 9 bits. So let's try to do this. So if I say that even parity makes the number of ones even, it means, let's count ones in this byte. 1, 2, 3, 4, 5. The number of ones is odd number. To make it even, we need to add extra 1. So that would be called even parity. And so let's see. So the sender actually sends 1, 0, 1, 0, 1, 1, 0, 1, and 1 at the end, extra 1 as even parity. Receiver received 1, 0, 1, 0, 1, 1, and this 0 was changed by noise to 1, so 1, 1, and 1 at the end. And the receiver takes the first 8 bits, calculates the even parity. Even means if the number of ones is already even, then there should be 0. If it's odd, there should be 1. So we count 1, 2, 3, 4, 5, 6. So receiver calculates that the last bit should be 0. It looks that the bit is 1, so it knows that all this message should be discarded because there is a bit error somewhere. And actually, receiver doesn't know which of these bits was changed, so it cannot correct this message. So I'll just remove this error correction away right now so you don't get mixed up. So the receiver checked the parity of the received byte. It sees that there is some error because it calculated the parity should be 0, but it's sent as 1, so there is a mistake. So it just deletes the message. This will be a little bit confusing, but the parity has two implementations. One is even parity and the other is odd parity. Basically, the odd parity is the opposite of even parity. Odd parity works in the following way. It counts the number of ones, and if it's even, then 1 is sent at the end, and if it's odd, then 0 is sent at the end. So for odd parity, the same byte that is sent, so we count ones, 1, 2, 3, 4, 5, it's already odd, so odd parity bit is 0. And it would be sent in this way. And in that case, the receiver would check it. So when using parity, you need to check out which way of parity receiver and transmitter is using. For example, in Termite, this is a serial receiver transmitter application for UART connection, and here in settings, we can actually select what parity we are using. None, which means that parity is not added at all, even, odd, and there's also mark and space. We're not going to talk about mark and space, but even and odd, you have to kind of select it. So if you're using an existing network, you would open its documentation and you would see what kind of error detection algorithm it's using. And if it's using, for example, even parity, then you configure everything for even parity. If it uses odd parity, then you configure for odd parity. Otherwise, the algorithm will just not work correctly and it will just discard all correct messages. Okay, so that is parity. You can also find extensive information about parity on the internet in this, for example, Wikipedia article, parity bit. So on every byte, there would be one parity bit, even or odd. So, you can find this information. Another way to calculate parity is doing XOR on bit by bit basis. So 1 XOR 0 is 1, here is also 1, 1, here would be 0, 1, 1, 1, and that's why even parity would be 1, for example. And in odd parity, it would be inverted. Okay, but let's now look at the bad side of parity. Parity is good only if you have 0 or 1 mistake. So either no mistake or just 1 mistake in the sent code. So right now, for the sake of example, we will continue using even parity. So odd parity is just for your information. It exists and you need to make sure that you are using the correct parity. But let's now look at the example and we will only calculate even parity. So let's say that the transmitter sends the same byte 1 0 1 0 1 1 0 1, and let's say there was noise which changed 2 of the bits. So this 0 became 1, and then we can choose any other bit. For example, the noise changed this one to 0. So when the transmitter sends these bits, it calculates even parity. It counts the number of ones, 1, 2, 3, 4, 5. It's odd. To make it even, we need to add one more 1 at the end. So now it's even number of ones, and it sends it. And the noise changes these 1 and 0 to 0 and 1 during the transmission over the air. And so receiver receives 1 0 1 0 1 1 sorry 1 0 1 0 1 0 1 1 1 0 1 1 and the parity bit 1, right? So 2 bits were changed, 1 0 1 0 1 0 1 1 1. Okay, this byte has 2 bits changed, so the contents are corrupt, they are damaged, but the receiver calculates even parity on this corrupt byte. It counts number of ones, 1 2 3 4 5, to make it even. It calculates that the parity bit should be 1. It then checks that the transmitter's parity bit is also 1, and the receiver thinks that this byte is okay. So parity actually is a bad error detection algorithm because it only detects 1 mistake or 3 mistakes or 5 mistakes or 7 mistakes. But if you have 2, 4, or 6 bits flipped, then the parity changes to the correct value and you cannot really detect the mistake. So um, saying it in probabilities, parity has only 50% chance of working and 50% chance of making false positive outcome. So parity has only 50% chance of catching an error, which is actually really low. Let's say you download a movie and half of the bytes have a probability that they're actually wrong, right? Using parity would be very dangerous, actually. So parity was used historically because it was really easy to implement in hardware, and it was the first simple, easy to use error detection algorithm. And if we think about it, if we have a channel which is very good quality, where bit errors are extremely rare, let alone 2-bit errors in the same byte, if the channel is really clean and good quality, for example, a shielded cable, then we could actually use this parity. We never have mistakes, but if we have this 1-bit mistake once in a lifetime, then the parity would catch it. So you need to select error detection algorithm according to the channel that you are using. For high quality, good channels, maybe you don't need error detection at all. Or if you want to implement, maybe parity is actually pretty okay because it's really simple. It's really fast. You just calculate XOR on all bits and you get the parity, and that's all. So parity is one method. There is an algorithm that I would call parity on steroids because it's still parity, which is simple to use, but we will modify it a little bit in the following way. So I will draw it here. let's say you are sending more than 1 byte. Let's say you are sending 8 bytes. 8 bytes is 64 bits. So now, let's say you're sending some bits, 10101101, something else, 000000000, 10101110, 0 11111101, something like that, and so on, right? And instead of adding parity to each byte, at the end, this parity on steroids algorithm would be calculating parity on each column instead of each row. Instead of each byte, you calculate parity on each column by virtually aligning these bytes this way. So now let's calculate, for example, even parity. 111, it's 3 ones. To make it even, we need to add 1. Here also, to make it even, we add 1. Here also, here again, here is 3 ones. Oops. This, this, this is 3 ones, this is 1011, it's again 3 ones. Here is 0 1, so it's an odd, it's an even number of ones, so it's 0. And here is 2 ones, it's already even, so even parity is also 0. So number of ones was odd, we add 1, and number of ones is already even, so we add 0. So, and then, so basically we send our information, then we calculate parity on each column, and then we send parity byte. And now what happens is if 2 bytes in one, if 2 bits in 1 byte are changed by the noise during transmission, then the receiver will calculate parity on each column. If it calculated on each line, it would calculate wrong parity. But because it's calculating on columns and each bit mistake happened on different column, then these parity bits calculated would also calculate to the opposite value, and there would be parity mismatch, which would be detected by receiver, and receiver would know that it has to delete the entire block because 2 of the parity bits in parity byte are wrong. Okay, to to kind of fool this algorithm, you would need that the mistake happens in 2 bytes at the same positions, and only then the parity would be calculated the same way. But what's the probability that noise strikes exactly at the same locations of 2 different bytes, or even, not even 2 bytes in a row, but 2 bytes in with 2 bytes in between? So in this case, the noise has less chance to fool this parity algorithm. So this column parity algorithm is actually relatively strong, I would say, because now even if you have 2 mistakes or 3 mistakes in a row, parity will change and it will be detected by the receiver. So you would need the mistake to happen in 2 columns, two places in the same column to fool this algorithm. So that is the parity on steroids. I would call it that way. Okay, do you have some questions about parity? You can write them in chat or you can ask them with voice. Okay, everything seems to be clear so far, yes? Let's see, chat. Okay, no questions. Fine. So parity is one method to detect errors. So if we use parity on byte by byte basis, it's bad. It's 50% chance to be fooled. But if we use parity on column by column basis, then it's good because errors need to happen to multiple bytes at the same positions, and it's much harder to fool such algorithm. Okay, so let's look at the next error detection algorithm, which will be called checksum. Parity was used in serial data transmission, but nowadays it's not used anymore even there. So parity was initially invented to work with short messages on byte by byte basis, but when Ethernet was developed, you know, the internet connection with cable internet connection, the messages that were sent over Ethernet were very long, right? So what are the two properties of parity? Well, first of all, it only has 50% error detection, and it adds 1 bit per byte. And how much is 1 bit per byte? It is equal to, and on the calculator we can calculate, so instead of 8 bits we send 9 bits, so the packet length increases by I guess 9 divided by 8. What's the ratio? It's plus 12.5%. So the message size increases by 12.5%. So the message becomes much longer, you know, 12.5% longer messages. So let's say you want to download the movie. The movie is, for example, 5 gigabytes, and you need to send extra half a gigabyte of parity bits to detect errors. You would agree that it's too much information that is sent redundantly. So for Ethernet, the error detection algorithm is called checksum. So the checksum works in the following way. Let's say you send a long message. I don't know, 1101 0010 11111111 102 110101. Oops. Let's say we send something like 20 bytes. Actually, to save some space, instead of writing bits, I will write just bytes in hexadecimal format. 0x12, 0x34, 0xab, 0xcd, and so on. So let's count how many bytes we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, let's say we have 10 bytes. So if we used parity, we would have 10 extra parity bits. But the checksum algorithm is pretty simple, and it works in the following way. It just adds all of these bytes together, calculating the sum of these bytes. So if one of the bits changes, the sum of all of these numbers, all of this data, will also change, and we can detect it. With a little catch, so whenever we have overflow, for example, the result is bigger than 1 byte, let's say we calculate checksum 8. It means that the sum is just 1 byte. So whenever we have overflow, we add this extra 1 to the beginning of our checksum. So it would work in the following way. So it's in hex 12 plus 34. I will use this calculator here. In programmer's mode. So, and the checksum in hex would be 1, 2 plus 3, 4 is 4, 6. This is in hex. I will just not write it in front of all of these 0x hex. So the next number to add, so this one we have, this one we have. Next is AB plus AB. So here I'll write plus AB is F1. The result is F1. Next is plus CD. Plus CD is 1BE. So it is BE. And the checksum algorithm, for some reason, not to lose this overflow, this 1, whenever it detects that we have extra 1, it adds it just plus 1 here. So we subtract 1 from the top and add 1 to the bottom. So instead of 1BE, we get just BF, right? So we add this extra 1 to the result so that we only have 1 byte at the output. So BF. That was plus CD. Next is plus 5, 5. Plus 5, 5 is again 1, 1, 4. So plus 5, 5 is 1, 1, 4. And we take this 1 and we just add it to this 4. So it is minus this and plus this. The result is 1, 5. So next we add 4, 8 plus 4, 8 is 5D. I'll continue it here. 5D plus 6, 5 is C2. C2 plus 4, 4 is 106, and this 1 is again added here, not to lose it, but not to kind of go over 8 bits. So it's just 7, 0, 7. So it's minus 1, 0, 0 plus 1 is 7. Next is plus again 4, 4. So 07 plus 4, 4 is 4b. And finally, 4b plus 5, 2 plus 5, 2 is 9d. So instead of adding parity after every byte, we just take this checksum and the sender puts it at the end of this message. It just adds 9d to the end, 0x9d. It adds 9d to the end, and it sends all of this data 1, 2, 3, 4, A, B, C, D, 5, 5, 4, 8, and so on, and 9d at the end. And the receiver receives all this string, and it also adds together all bytes. Whenever there is one overflow, it's added to the bottom, and it adds them all together, and then it checks if its checksum was also 9d. It means that this message has no mistakes. However, if there was one bit wrong, then of course the sum of all of this message will also be different. The checksums will not match. So the receiver will know that there is a mistake, and it will just discard all of this message, or maybe send back that there was a transmission error or something like that. So that is checksum. So I showed you checksum 8. In Ethernet, I think it's actually done as a 16-bit or 2-byte checksum. So basically what that checksum does is it treats the bytes in pairs. So instead of 1, 2 plus 3, 4, it thinks that this is one number, 1, 2, 3, 4. The next number is A, B, C, D. The next is 5, 5, 4, 8, 0, 6, 5, 6, 5, 4, 4. And if there was an extra byte, if the number of bytes were an even, an odd number, it would just probably add 0, 0 at the end to make it even. So this is how the checksum works. And since checksum adds these things together and adds the overflow bit also, you know, checksum is stronger than parity, and it's actually still easy to calculate. It can be calculated online. As we receive byte by byte, we can in parallel calculate the checksum. We receive a byte, we add it to the checksum. We receive next byte, we add it. So we don't really have to wait until we receive all of the message and then we start from the beginning to add the numbers. We can calculate the checksum online real time during the stream. Okay, so checksum is pretty good with that. Parity with columns and rows, maybe not so good. You need 8 separate parity calculators in parallel, so not that great of an algorithm. So checksum was, of course, uh, adopted. So let's search on the internet. There is also an article in Wikipedia about checksum and about its algorithms. So, and this checksum is used, for example, in Ethernet. So let's write in Ethernet frame. It's possible that Ethernet has been updated, but I'm pretty sure hash code. Hash code. It doesn't really say that. Uh-huh. Hmm. So this Ethernet frame, and it should have checksum in the header. Okay, so that is the second algorithm to calculate error detection. With this algorithm, we can detect errors. And now let's look at the third method, which is actually, I think, lately the most widely adopted. And now let's also analyze um, the impact of checksum for compared to, for example, parity. So checksum error detection, I would call it strong. It's hard to calculate, but generally, these bit errors would need to appear multiple times to make two checksums equal for different uh, messages. So I would say, I would just simply describe it as strong. There are some mathematicians who have analyzed it deeper and have come up with some numbers about how strong the checksum is. But for messages of several kilobytes, checksum can be considered pretty reasonably okay algorithm. Strong error detection, only one byte or word or double word um, added to message, right? So the checksum only produces one extra byte or pair of bytes or 4 bytes, depending on which checksum version we are using. Unlike parity, which adds 12.5% more bits. So for example, if you want to send a message that has 100 bytes, you add only 1 byte extra, which is only 1% longer message than the original one. You want to download a movie, several gigabytes, and you only send something like maybe 10 kilobytes of extra information. Okay, do you have some questions about checksum? You can also ask them in the chat box. Okay, so the next thing that we need to talk about is Cyclic Redundancy Check. It's written short for CRC. Cyclic Redundancy Check. Since Cyclic Redundancy Check is considered probably the strongest algorithm between these three, and since it is basically nowadays used everywhere instead of checksum or parity, parity and checksum are considered to be old school, obsolete methods, then nowadays, mistakenly, many people call all of these error detection algorithms CRC, but actually CRC is short only for cyclic redundancy check. And cyclic redundancy check algorithm is basically an algorithm that works on integer division as the basis. So CRC, cyclic redundancy check. So cyclic redundancy check, error detecting code. And it works in the following way. You have a message that you want to send, and the algorithm just divides the input with some predetermined constant divisor, and it divides, and it calculates the remainder on the division, which is the cyclic redundancy check result. Okay, it's hard to show you an example by hand because, you know, decimal division is complicated. Binary division for humans is even more complicated. So I will not show you like an example, but generally, uh, it's an integer division. You take the input, you treat it as one long line of ones and zeros, doesn't matter, it can be several kilobytes or megabytes of ones and zeros, and you take some small number with which you start to divide, and you just divide the input until you get the remainder, which is your cyclic redundancy check result. And, you know, you can write. The good thing is that this division algorithm can be converted mathematically to just XORing and shifting bits. So for example, here is CRC32 algorithm. CRC32 means that this divisor is 33 bits, so the remainder will always be 32 bits. So the result will be between 0 and 32 bits. And so here is the algorithm, which basically has input bytes. Since it is 32 bits, it can treat bytes as bytes, not single bits. You first initialize it to all ones, and then you can use a lookup table to find the division of input and this divider. And then you end them with 0xFF. Then you XOR them again with the lookup table value, with this thing shifted by 8, and do it for all bytes, and then the result is CRC32. So basically what you would do, you would find online CRC32 algorithm code, and you can just copy and paste it into your project. For example, 32 C library. And here you have even a written code. So basically, you could do it mathematically by dividing the numbers, but since there's a limited number of combinations that you need to divide, then these divisions can actually be pre-calculated and saved into this lookup table. And instead of doing the actual division, you can just check what's the input and just, you know, for certain number, you can look up in this lookup table what's this number divided by the other number. You don't have to do the division mechanically by yourself. You can create this lookup table and just see, okay, so input is 1101, divisor doesn't change, it's constant. So you just look, okay, for this input, what's the division? And you find it. And then you take the next part and you look it up, you find it, you insert it. So it can be calculated pretty fast. And this is a table with, I guess, 256 values for all possible input byte combinations. So in this example, it's 4 bytes, but in reality, it's worked on 8 bytes at a time using this lookup table. So cyclic redundancy check is now used basically everywhere. You see in this example code, for example, you have this lookup table and the actual algorithm, which is really short. And cyclic redundancy check has the positive feature that it can be written as a short code with a small lookup table. And it can also be easily implemented in hardware. So you can make a hardware cyclic redundancy check calculator schematic, and it just calculates the result on stream, which is really powerful. So cyclic redundancy check is used nowadays everywhere based on integer division, and it is considered stronger than checksum, and it also only produces one extra byte or word or double word at the end of the message, depending on which cyclic redundancy check option you have selected. Now, you might want to ask, okay, so we have input ones and zeros, some message that we want to send. How do we select this divisor? Are there some better divisors and some divisors and some worse? Yes, it's true. And this is why we have these scientists called, I don't know, mathematicians, I guess, who have tried all kinds of divisors, and they have found out that some of them produce a very strong uh, remainder, which is very prone to bit swaps, bit changes, bit alterations. And you can, for example, look it up in this same um, Wikipedia web page. And here is a table with some widely used um, polynomials that are used as divisors for the cyclic redundancy check calculation. Because, for example, we could select this divisor as, 0, 0, 0, 0, and then the output is basically infinity and it doesn't work. We can select divisor as 0, 0, 0, 1. Dividing anything with 1 will produce the same thing. So, it doesn't really do anything. But the scientists have tried many kinds of CRC divisors, and here are some which are actually used in certain algorithms. For example, in mobile networks, the divisor is this: x to the power of 3 plus x plus 1 is just a fancy way to say that the first bit is set, the second bit is set, and the fourth bit is set, and it's only in it works on, for example, this cyclic redundancy check 3 means that it works only on I guess 3 bits at a time, right? So this is why it's really short. The CRC1 is just I think it's the same as parity, as even parity, but we don't really use these. We are interested in CRC with 8 bits. And as you can see, here is CRC8. Here's also CRC8 for Bluetooth. Bluetooth, for example, uses divider in this form. And, other values. There's also, for example, CRC16. For example, this DNP is used in MBus, which is meter bus, popular bus in Europe, and its polynomial is this. And for example, very popular, widely used is this CRC32, which is used in Ethernet. It's used in many other algorithms. It's often simply just called CRC32 or checksum, and its polynomial is this. So the number of bits tells you how long the result will be. So for example, if you use CRC32 on your message, it will add 32 bits at the end. And of course, as you can understand, the longer the CRC, the less chance there is for mistakes, for false positives. So, and also, if you have long message, you want to use longer CRC. If you have very short messages, you don't have to put 32-bit CRC on 4-bit long message. So if you know that your network only has short messages, you can just use CRC8, for example. you only add 1 byte on a couple of bytes. If you have longer messages, you use longer CRC, for example, CRC 16. If you have very long, very big data, you use CRC 32. And how to know the length of CRC to select? Um, Actually, I cannot really tell you that. Let's see. It's hard for me to tell you that, but for example, what I have heard is that you use CRC8 on messages that are up to 64 bytes long. I don't know, I don't have any mathematical proof. It's just what I have heard from professionals that were working on this field. So CRC8 you can use if your messages are something like 64 bytes, for example. You know, short messages, for example, car remote, which sends a signal to car to unlock the door or lock the door. It consists only of few bytes, so they would use CRC8. They wouldn't really use anything longer. If you have messages of up to a couple of kilobytes, you can use a 16-bit CRC. And for longer messages, CRC32 is sufficient. For example, when Windows writes a file into the hard drive, it divides the file into small chunks of a couple of kilobytes, and after each kilobyte, it adds also a CRC, and then it reads back the result from hard drive, compares that the CRC written matches the data, and for example, if it doesn't, then it tries to write the data again in different location in hard drive, and that's how Windows makes sure that your hard drive only contains good, high quality, precise, valid data. If Windows didn't check CRC and didn't check what it wrote also matches what was written, then computers would be very unreliable. So CRC32, I think, is also used in hard disk uh, data. Let's see. I think it should be written there. Okay, here's FAT. Um, Maybe it's not really said here, but that's how these hard drives work. Maybe I can't find it right now, but fine. Okay, so this is the checksum. Okay, and you know, generally I can just copy the description of checksum and paste it here about cyclic redundancy check, because they're really similar. It's just that cyclic redundancy check is considered to be stronger than checksum, maybe also easier to calculate, easier to implement in hardware, faster. So cyclic redundancy check has taken over the world, and checksum isn't really used that much anymore. So do you have some questions about CRC, Cyclic Redundancy Check algorithm? You can write it in the chat box. Okay, if you don't have any questions, then the last method of error detection is hash algorithms or cryptography. So cryptographic hash functions. So Cryptography for error detection could be considered as extension of the cyclic redundancy check. But instead of simple integer division, cryptography algorithms usually are much more complicated, and they use other non-linear functions, non-linear transformations, and usually they are irreversible. It's impossible to calculate back or forge the data. For example, in cyclic redundancy check, everybody knows that it's, for example, CRC32. And if you send the data, the receiver can calculate its own cyclic redundancy check. It can also manipulate the bits in such a way that it gets the necessary cyclic redundancy check. And generally, cyclic redundancy check is good, but it's not secure. A hacker can catch the message, change some bits in the contents, also recalculate the corresponding cyclic redundancy check, and send it to receiver, and the receiver wouldn't even know that somebody has tampered with the data. It wouldn't even know that the hacker actually caught the packet on air, changed the data, and sent it again to receiver, right? Okay, in air transmission, maybe it's harder to do, but in cable transmission, the hacker can just cut the cable, put his listening device in between, catch the transmitted packets, change them, and send over the other end of the cable to the receiver. So cryptography algorithms are non-linear and usually irreversible in such a way that it's hard to edit the values and get the hash to match. Okay. So for example, oftentimes if you want to download the program, you can download it, but the program creators also publish the hash of the program, so you can check that during the download somebody didn't edit the bits and didn't send you a virus. I think that the most SourceForge programs have this thing, so you can like double check it. And let's see. So we will go deeper into cryptography in other lessons later in this course, but generally there is, for example, this old MD5 standard, or SHA1, SHA2, SHA3 as well, and they are considered strong hash algorithms. But kind of the disadvantage for our low-level application is that usually hash algorithms are slow to calculate. You cannot just simply do a little bit of XOR, a little bit of addition and subtraction, and get the hash value. Usually these are non-linear complicated functions. They use elliptic curves or long polynomials, or maybe some lookup tables to calculate the output, and usually the output that is created is a long. For example, SHA creates 20 bytes. So our cyclic redundancy check made maximum 32 bits. For example, if we use CRC32, it's just 4 bytes. This thing generates 160 bits or 20 bytes. Maybe you're only sending a message that is 10 bytes long, and SHA creates 20 extra bytes. So, for data transmission, this thing, not very practical. MD5 creates 16 bytes, for example. SHA2 creates, depending on the version, you can have 256 or 512. It produces, for example, you can see it here, 32 bytes, 48 bytes for this version, or 64 bytes for this version. So it creates a lot of extra bytes. So the chances of a bit error creating a correct SHA is almost zero, but you are paying for it, for this security, for this low level of errors by lots of bytes added at the end of the message. So cryptography, without going too deep into the topic, which we will look at later, we could say that it's strongest, very small probability for errors to go through undetected, almost, almost zero, but it has the largest overhead. To extent, parity can create even larger overhead. So I will just write strongest error detection, tens of extra bytes. For example, 20 to 64, as we checked. 20 to 64 bytes appended to the end of the message, right? But chances of collision, chances that the bit changes, but the result doesn't change, very slim. Cyclic redundancy check is also prone to some errors. In this cyclic redundancy check message, you can change some bits in the middle of a message, and maybe the cyclic redundancy check calculates to the same value. In cryptography, it's much, much less possible. So we actually have written these things in ascending order historically, and also ascending order in strength. So usually for low level applications, everybody just uses cyclic redundancy check. Okay. So do you have some questions about this topic? You can ask them in chat box or using your voice. If not, then that is all for today. Next time we will look at error correction algorithms.